Hey YouTube! So last time we looked at the derivative and defined it formally as a way of answering the tangent line problem. Essentially, can you find the slope at a point on a function f of x? So I'd like to take some time really quickly to go over a rudimentary example of how to apply this. So we are actually going to, instead of just finding the derivative or the tangent component, the slope, we're going to find the entire equation of the tangent line that's tangent to the function at a certain point, x equals 3. Okay, so in order to start this problem, in order to find the equation of any line, you need two things that you should know from algebra. At the very least, you need a slope and a point. Okay, so if you were given 2 points, for example, x1, y1, x2, y2, you could find the slope of those 2 points, and then use point-slope form in order to determine the equation. And then maybe write it in y equals mx plus b slope-intercept form. But you need a slope and you need a point. Well, if I'm dealing with the tangent line, you know that you're going to deal with the derivative as something that's synonymous with slope. So the first thing I'm going to do is I'm going to differentiate this function. So in order to do that, if I want to find f prime of x, I'm going to be taking the derivative with respect to x, these guys mean the same thing, of this function. So I'm going to actually rewrite this function. Instead of x squared divided by cosine of x, I'm actually going to realize that 1 over cosine of x is actually secant of x. So the reason I'm going to do that is so I can write it as a product instead of a quotient. Because in my opinion, I think the product rule is much more intuitive and straightforward than the quotient rule, because you don't have to memorize low d high minus high d low, square the bottom away we go. You just have to add two things together. Okay, so I'm going to rewrite this as secant of x. Maybe you don't remember the derivative of secant of x, but you really should. So if I differentiate this, according to the product rule tells me that I take the first term, x squared, times the derivative with respect to x of the second term, secant of x, plus the second term, secant of x, times the derivative with respect to x of first term, x squared. Alright, so last time I defined 6 transcendental functions and talked about their derivatives, and they were the trig functions. Okay, so the derivative with respect to x of secant of x, if you don't remember that, I would memorize it, but that's actually just secant of x times tangent of x. Okay, so this is actually equal to x squared secant of x, secant of x, times tangent of x, secant of x. Rewrite that. X squared secant of x, tangent of x, plus the derivative with respect to x of x squared. Well, that's a simple power rule, right? So if I have an exponent of 2 and I bring that guy down, well, 2 serves as my coefficient. So I have 2 times x to the first power, so just 2x, times secant of x. Okay, so that is my derivative. That's my first derivative. If I plug in any x value, I will get the slope at that point. Okay, well, I have an x value. I have x equals 3. So in order to evaluate what the slope is, I just plug in f prime of 3. So I take this equation, and everywhere I see an x, I'm just going to put a 3. So this would be 3 squared, which is 9, secant of 3, tangent of 3, plus 2 times 3, which is 6, secant of 3. Right? And that is the slope of this tangent line. But the problem asks us to find the equation of the tangent line. So really quickly, if I drew some sort of a picture, and I had a function, we found the slope of that function at that point. Well, if I want a point, the only point that I'm viable to pick is this x value right here. So whatever this x value is plugged into the function would be my y value, and from that you can determine this point. Because by definition, a tangent line only touches the graph at a single point, the point of tangency. So you have to use x equals 3 to plug into your function. So if I do that, I'm going to take this x equals 3 value, and I'm just going to find f of 3. Okay, so when I say f of 3, I am not going to plug 3 into this equation. That's redundant. We already did that. I'm going to plug 3 into my original function to determine the y value. So f of 3 would be equal to, well, 3 squared is 9, And I'm just going to rewrite this again as secant of x, so secant of 3. So that's my y value. So if I'm looking for a point, my x value is 3, and my y value is 9 secant of 3. So if I want to put these guys together, I'm going to use point-slope form. And I'm going to say that this is equivalent to, well, if you don't remember point-slope form, I'll go over it in just a second. But that's essentially y minus y1, so my y-coordinate of my point, 9 secant of 3. And that is equal to m, so my slope, which is this junk. So that's 9 secant of 3 tangent of 3 plus 6 secant of 3. Okay, so that is my slope times x minus my x-coordinate, which is 3. Right? I'm not going to bother simplifying this. Oh my god, please don't simplify this. Don't distribute that and add 9 secant of 3. A lot of teachers are completely fine with you leaving it in point-slope form for this very reason. Okay? If it's homework, then simplifying this is unnecessary. Okay, so that would be my equation of the tangent line at the point x equals 3. So if I wanted to generalize this, I want to generalize what I just did, and to find the slope or the equation of any tangent line given some x equals c value, let's go ahead and talk about that. So I want to compare what we did in pre-calculus to what we're doing right now in calculus. So I want to speak in general. Given a function f of x, okay, tangent line at some point x equals c is given by the following. Okay, so in pre-calculus, we learned, oh, I only need two things to find the equation of any line. I just need slope and a point. So slope was just given by m, which was also the change in y over the change in x, which you can write as delta y over delta x if you want. All right, and the point, just any point you want. Because on that line, you only need 2 points technically to define that line, but a line has an infinite number of points to choose from. Okay, so just any arbitrary point, we'll call it x1, y1. Okay, and from that, we determine that the slope of that line is well, it's y minus y1 equals m times x minus x1. Okay, and in actuality, if you want to plug in m equals this quantity right here, you'll get the exact same thing. You'll get y minus a specific y value, just like here you'll get y minus a specific y value if you plug that in. All right, so how does this transfer to what we're doing right now in calculus? Okay, so this is the slope in pre-calculus. In calculus, we do the same exact thing. It's just that we're limited in terms of the number of points, which in my opinion is actually a good thing, because I don't have to be picky, and I don't have to choose the ideal point. I only have one option. Okay, so the slope in calculus is the derivative. It's dy dx. And I'm going to signify something a little different. I'm going to say it's dy dx. I'm going to draw a line right here and say at the point x equals c. That means I'm finding the derivative at this specific point. It's just another way of notating it. Okay, but this is exactly equal to the more common notation, which is f prime, the derivative at x equals c. Because f prime of x is the slope equation. For any x value, I'll find the slope at that point, but I want to plug in c. All right, so what's the point that I'm dealing with? Well, in our example, it was x equals 3. Right here, I wanted the equation at x equals 3, and I plugged that into my function to determine the point of tangency. So a lot of times you should be given a c value. So whatever that c is, you plug that into the function, and you'll get an x. Your x value is c, and your y value is f of whatever c is. All right, so using this format that you discovered in precalculus, we can write the equation of a tangent line as y minus y1. Okay, in this case, our y coordinate is f of c, is equal to m, which is our slope, denoted f prime at c, times x minus x1. Well, our x coordinate is just c. So I'm fine with this. Some people like moving f of c over to the other side, so this would be y equals f prime of c times x minus c plus this quantity f of c. And that represents the slope, or the equation, the equation of a tangent line at this specific point. All right? So I want to go through an application, and I think this is a really cool application. Okay, so the question that I want to ask is, so on a graphing calculator, you can find x-intercepts extremely easily. So x-intercepts, or roots, are called zeros or solutions. How do they find those? How do they approximate them to so many decimal places? So I want to go through that really quickly because I think it's really cool. And it also applies our knowledge of derivatives and tangent lines to approximate this. So let's say I had a linear function. Let's start small. If I had a linear function, well, a linear function standard form is probably something like ax plus by equals some number c, where x and y are the variables, a and b are the coefficients, and c is just whatever the function equals. So if I wanted to find the x-intercept of this, well, remember that an x-intercept is anywhere where y is equal to 0. So if I plug in y equals 0, I get exactly where it touches the x-axis. Right? Because if I had a coordinate system like this and y equals 0, I'm essentially saying there's no vertical component. I'm exactly right here. So I'm looking at all places right here on the x-axis where my function touches. Okay, so for the x-intercept, y equals 0, so I'd essentially have b times 0, which is 0, and I'd be looking at ax equals c, or x equals c divided by a. So of any line, this would represent whatever my x-intercept is. Okay, let's suppose that I wanted to move one step up instead of a degree 1. Let's talk about a degree 2, so a quadratic function. All right, I'm pretty sure all of you know what's coming right now. If I asked you to find the solutions of a quadratic equation, and you couldn't factor, you couldn't group, you couldn't do any of this other stuff, you had to use one thing that works every single time. I'm sure all of you are going to cry. It is the quadratic equation, right? So that's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? And you can derive this if you really want to. I'm not going to show it, but if I gave you something like ax squared plus bx plus c equals 0, plug that in. Plug that in everywhere you see an x, and you should get this to equal 0. With a lot of manipulation, I find that it's easier to go from this form to the standard than backwards. So if you want to work from here, you can actually derive the standard form of a parabola or any quadratic function. Okay, so that's the solution. That'll give you at most 2 points that intersects the x-axis. Okay, but what if I have more than 2 terms and I can't factor? I can't use this nifty trick. I can't use the quadratic formula. How am I going to estimate that? Okay, so the answer to this question is actually something called Newton's method. Okay, so I know Sir Isaac Newton is popping up a lot in this course. He kind of co-invented calculus. He's kind of a big deal. Okay, so Newton's method is going to allow us to estimate. Sometimes this is called the Newton-Raphson method, after the other guy that kind of helped with it. But essentially what it's going to do, well, it's going to let us approximate the zeros of a function. Okay, so first you're going to have some sort of an initial guess. and we'll call that x naught. Okay, so it's just some sort of an x value that it looks to be close to. Okay, so this initial guess, and it will be clear in just a few minutes when I show you a really nice picture, but you're going to use an initial guess, we'll call it x naught. Use that to determine a better guess. Okay, so technically what I'm going to show you is all approximation, but you're going to come to find that this is actually a really, really good approximation, and graphing calculators do it all the time. So let me just draw a picture for you. So let's suppose I have a situation. I have a function. And I want to approximate the 0 or the x intercept of that function. Now obviously there are 2 x intercepts, and there can be as many as, well, however many is the highest degree in your polynomial. So if I have an x to the 6th, there could be up to 6 x intercepts, which is why you need that initial guess. You want something fairly close to what you're approximating. So if I pick something right in the middle, I don't know whether the tangent line is going to be closer to this x intercept or this x intercept. So pick an initial guess that's fairly close to it. I'm actually going to be perverse, and just to show you, just to exaggerate the difference, I'm going to suppose that this guy right here is my initial guess. We're going to see what it comes out to be. So let's say that I want to find the x intercept of this function, so I'm going to use this as my guess. All right, now that's an awful guess, but with calculus you can actually approximate this to be closer, much, much closer, by taking the derivative at this point and from that deriving the equation of the tangent line. So eventually, and you know how to find the equation of a tangent line, we just went over that. So if I find some sort of a tangent line, what I'm going to get is something that looks a little like this. So that is my tangent line. Okay, and you can see that tangent line hits the x-axis at something that's really, really close to what it actually is. Okay, so in this case, let's say that I am approximating this guy, just for reference. So this tangent line, okay, well, this y coordinate is f prime of x naught, my initial guess. I'm taking the derivative at that initial guess to come up with the slope of this line. And then I can use methods from before, and I can take this number divided by the coefficient of my x term in order to find the x-intercept of that line. Pretty easy. And after I find the x-intercept of that line, that's going to be my first guess. Okay, so we're going to call that guy, well, I don't know, we'll call it x1. Instead of x0, we'll call that x1 for my first attempt at a guess. And of course, you can do much better than this. So what you're going to do now is, so here we took x naught and we plugged it into our function. We're going to do the exact same process. This process is called iteration, where you do this multiple times in order to really, really get closer to whatever this x-intercept is. So I'm going to plug in x1 to my function. Okay, so maybe I should do this in a different color. I'm going to plug in x1 to my function. It looks to hit about at right there. So now I'm going to find the tangent line at this point. So this guy is f prime at x1. I'm going to find the tangent line of this guy at x1. So to do that, tangent line looks like it's doing something like this. So you can see that within 2 guesses, we've actually come so very close that you probably on the video can't even tell that there's a difference. It hits the x-axis at something that's so close to this point that we might as well just say that's the x-intercept. Okay, so I'm sure graphing calculators do this several times to get an approximate, and it keeps moving decimal by decimal by decimal until it gets like 10 decimal places, and that's how a graphing calculator determines the roots, the solutions, or the x-intercepts of your function. Okay, so how do I put this in algebraic terms? Okay, so suppose that I'm in this situation, I'm given a function f of x, and we'll say initial guess x naught. So let's see if I can't mathematically map out exactly what my process was here. Okay, so before I do that, I just want to define something really quickly. So we obviously had more than one guess, and the more guesses you do, the more you converge on to whatever the x-intercept is. So that process of repeating it, well, that's called iteration. So I'm going to go and denote that, because it is a word that's going to pop up fairly often. I know it pops up in computer science. So the process of going over this several times. And then we're going to work an example problem. Okay, so I just like the word iteration. I think it's nice. All right, so let's see if we can't algebraically see what we were doing here. All right. So the first thing that I did was I took my initial guess and I determined the derivative at that point. Okay, but furthermore, I actually determined the equation of the tangent line formed with that initial guess. So we can do that. So for some x naught, the tangent line, we already kind of defined that. So the tangent line equation would be y equals f prime at x naught times x minus x naught plus f of x naught. The only thing from that that's different than this guy is that this guy had c, and instead of c, I'm defining my c value to be my initial guess x naught. Okay, so that's my tangent line, and I want to determine the x-intercept. So if I want the x-intercept, hey, I just make y equal to 0. So if I want the x-intercept, I set y equal to be 0. So here, 0 equals f prime of x naught, x minus x naught, plus f of x naught. Okay, so I'm going to subtract this guy over, because I want to find out what my x value is. Given a y value of c, I want to know what my x value is. So I want to solve for my x. So I'm going to subtract f of x naught from both sides. I'm going to divide by f prime of x naught. So I'll do that in one step. I'm going to subtract some minus f of x naught divided by f prime at x naught, and that equals x minus x naught. Okay, finally, to get x by itself, I'm just going to add my initial guess. This is actually x naught minus f of x naught divided by f prime at x naught. And this should kind of make sense. So you're going to take whatever your initial guess was, and you're going to compare the function value with the first derivative, and you're going to subtract that off. So these should be relatively close. Okay, obviously they're going to be closer together the more iterations you do, but this is going to be fairly close. So you're going to subtract off a tiny amount to get closer and closer to the actual value of the x-intercept. Okay, so this represents your x value. And instead of x, that's not what x equals technically, that's a better guess for x. So I'm going to call that x1 to symbolize that we used an initial guess x0 to get a better guess x1. Okay, so hypothetically, if I wanted to repeat this exact process and use x1 in the same process, because in my picture I did this twice, well, hopefully you can see that the second guess for x is just the first guess for x minus f prime at, or sorry, minus f of x1 divided by f prime at x1. So it's the same thing, just you're solving for a different variable and you're using a different initial guess. But it's the same exact process. Right? So I'd like to do an example really quickly. So we were given this problem. Use 2 iterations of Newton's method to estimate the zero between x equals 2 and x equals 3, because this touches the x-axis at 3 points. Can touch it out at a maximum of 3 and it hits all 3. So I went ahead and graphed it for you because I'm such a nice guy. X cubed minus 3x squared plus 2 is our function, and we want to estimate this zero right here. So it's between x equals 2 and x equals 3. Okay, so the first thing I'm going to do is I'm going to look for my initial guess. Well, I don't know, it looks to be pretty close to x equals 3, so let's use that as an initial guess. Okay, so our x naught, if you're a formula person, equals 3. Okay, but what am I actually doing? Well, I'm taking this initial guess and I'm plugging it into my function. Okay, so at this point right here, I want to find the tangent line at this point. Right? And from that tangent line, I'm going to derive an X intercept that's going to be pretty close to this guy. So that's one iteration of Newton's method. So I'll go ahead and use the formula that we derived over here. So I'll go ahead and say that my guess x sub 1 is going to be equal to my initial guess x0 minus f of x0 divided by f prime at x0. My apologies for messing that up, by the way. That's not a subscript of 0, it's a subscript of naught, but looks like a 0, so I'm just going to say that. Okay, so we want to find f of whatever this is, so f of 3. Well, my function is x cubed minus 3x squared plus 2, so if I want to find f of 3, I take 3 cubed, which is 27, minus 3 times 3 squared, that's also 27, plus 2. Okay, so I get 2. Yes, sorry. Yeah, so I would get 2. And then my derivative at x0. So if this is my function, my derivative of x is equal to, well, I'm just going to use the power rule several times. So that's my exponent. I bring that down as a coefficient. That would be 3x to the second power. Okay. I can take this coefficient out and bring this exponent down as a coefficient. So this would essentially be negative 3 times 2 for my new coefficient of negative 6, x to the first. And since that's a constant, and you take the derivative of a constant, that goes to 0. So that's my derivative. Now I want to plug in my initial value of 3 to determine what that is. Well, f prime at 3 is just 3 times 3 squared, which is also 27, minus 6 times 3, which is 18. Okay, so that's going to get me 9. Okay, so essentially what I have here, so f of 3 was 2, f prime of 3 was 9, so this would be equal to my initial guess 3, don't forget that, minus 2/9. So 3 minus 2/9 ends up being 25/9 for my first guess. Alright, so I'm going to show you the process, the setup method, and the final answer for doing this again, but I'm not actually going to do the computations because it's going to get really, really messy. Alright, so I actually ended up doing the work for you. So if you plug in your first guess of 25/9 into this equation, well, according to Newton's method, your second guess is going to be this first guess minus the comparison of f of 25/9 divided by f prime of 25/9. So I went ahead, evaluated all of that for you, and I got an answer of 2.733756. So if you want to look at what the actual answer is, the actual answer can be computed using, well, I don't know, the cubic equation or some complex analysis that honestly is not worth it. But the actual answer is about 2.7320508. So our second guess was only off by what, 1,000th? So if you want to compare each of these answers individually, I went ahead and did that. So our initial guess of 3 is actually within 91% accurate. So just by eyeballing it, you're within 10% of what the actual answer is. Okay, so your first initial guess, let's see, that bumped it up to 98%. So here you're within 2%. And this answer right here, just by using 2 iterations of Newton's method, you're within, well, 99.9% accurate. Okay, that's a whole lot. That's amazing, actually, considering you only did this 2 times. So I wanted to point that out. Okay, so just as a 20-second recap of what we did, we wanted to find the 0, this specific 0 right here. So we had an initial guess at about 3. We eyeballed it. And said if we plug that into a function and find a tangent line, okay, the equation of the tangent line, tangent to that point, is going to give us an X intercept that's really, really close to what the X intercept actually is. So then we used that X intercept and plugged it into the function and repeated the process to come up with a value that's within 0.1% accurate, which is actually really good. Okay. All right, so I want to talk about one more thing, and that's essentially another way, a really good way of looking at the derivative. It's a unique way called the differential. So the idea is to look at a change in the x value and look at how that affects the change in the y value. So before dy dx, or any slope value, gives you a comparison of those values automatically. Okay, but we want to isolate one of those and see where that gets us. So if I have a function, draw my favorite picture, what you understand to be the derivative is actually taking this point right here and finding the tangent line. Okay, so it's going to look something like this. Okay, and we approximated that in the beginning using a secant line. So let's suppose that I have a secant line, okay, that essentially cuts this function into 2 points. Okay, so it's going to look something like that. And if I wanted to find the slope of this secant line, well, what you're essentially going to do is you're going to take these 2 points and compare the change in the y, which I'm going to denote as delta y, and compare that with the change in the x, the delta x. Okay, so the slope of the secant line ends up being delta y divided by delta x. And if I wanted to, I can actually take this a step further and look at what does a change in y actually mean. What is my function doing? How much is my function changing? Well, if I multiply both sides by delta x, I get that delta y is actually equal to this slope times delta x. And from this, you can derive point slope form. I think I stated that before, but by taking a change in y, so 2 y values, we'll call it y and y1, and just subtract them to find the change. And take 2 x values, we'll call it x and x1, and look at their change. So this is the idea that I want to focus on as what you've discovered in Precalculus, that you can take a change in x, an actual distinguishable change in x, a difference of horizontal between 2 points, and look at how the change in y is affected by that. So in calculus, what we do is we take this slope and we find some sort of an imaginary change in y and compare that with an imaginary change in x. And we use the idea of the derivative as taking the secant line as it approaches closer to the point of tangency. But essentially, we can't call this delta y because there is no change in y. So we call it dy to stand for the differential of y, the infinitesimal change in the function. And likewise, we call this dx to denote an infinitesimal change, or an infinitely small change in the horizontal. And we compare those for the idea of the derivative. So if I want to find the slope of the tangent line, I compare dy and dx. So if I wanted to, maybe I could go through the same process. If I wanted to know how much my y value changed at a given point, well, if I multiply both sides by dx, I could get that dy of itself is equal to the slope, which I'm going to denote as the derivative, so f prime of x times dx. And this is the idea of differentials. So what I would actually say is this guy is the differential of y, or the infinitesimal change in my function, and this is my differential of x. Okay, so I want to make a quick note about differentials. So technically, like if you're a math theorist, this expression is meaningless. Why is it meaningless? Because dy and dx are both changing at infinitesimally small rates, and they're approaching zero. And the only way to discover what they equal is to compare how fast how fast your y value is going to zero, and how fast your x value is going to zero, because they're both going to zero. So essentially, dy is technically supposed to be 0, dx is supposed to be 0, but since they're approaching 0 at different rates, the only meaningful expression is to compare dy and dx for a slope. But around a point, we like to say that we can isolate this change in y if we know what the change in x is at a given point of tangency. All right, so let's go through an example really quickly of what we can do with differentials. So let's suppose that I wanted to approximate the value of the square root of 15.9. Because, I don't know, you lost your calculator, or you weren't allowed to use it, and you wanted to approximate this function value. Okay, well, just using some logic, I know the square root of 16 is 4, and since this input value is slightly less than 16, I would expect my answer to be slightly less than 4. All right? But how less than 4 is it? Well, we're going to use differentials to calculate it. So the first thing I'm going to do is compare this to a function, right? Because calculus is all about taking a set of data values and using that to come up with a function, and then using derivatives and integrals to actually apply that. So what I'm going to do is I'm going to suppose a function f equal to the square root of x. And I'm going to say that I can input any x value that I want, and I can output a value. So in this case, I'm inputting 15.9, but I also know for sure, at least I hope we know, that the square root of 16, inputting 16, will give me an output of 4. So what I know right away is if I draw the square root of x, it's going to look something like that. And if I plug in 16, I get an output of 4. Well, if I isolate the neighborhood around 16, and I take this guy and magnify it, so I'm going to take that neighborhood and I'm going to amplify it up, what we essentially have is this change, okay, where maybe this is 15, and maybe this is 16. And I want to look at this point right here. So we are going to use the idea of differentials, but just to go back to what we started with in the beginning of this video, let's use tangent line approximation. Let's find the equation of this tangent line and use that to localize a value for 15.9. Because if I find a line, I know for sure 16 is going to be on that function. 15.9 is going to be really close to that line. So whatever I input 15.9 for that line is actually going to be really close to what it is on the actual function. Okay, so first, I'm going to use a line, a tangent line, to approximate it. To approximate f of 15.9. Okay, so I'm gonna call the tangent line g of x. Let's call it g of x. So if I want to view the tangent line at 16, well, let's say that it looks a little something like this. Right? I didn't exactly draw this to scale, but you can kind of see where I'm going with that. So that's my tangent line g of x. Finding the equation of that tangent line is going to allow me to plug in values really close to 16 and get something pretty accurate. So if I went ahead and did that, what I would find is that this tangent line g of x, well, I know that it's going to be y minus my function value at c, f of c. That's going to equal my derivative, so f prime of c times x minus c. So what does that end up being? Well, if you look at my picture, if I use the idea of the derivative, I know that that 16 is going to be my c value. And I know that if I plug in 16, I get 4. And that's a point. That's the only point because of the point of tangency. So I know that my point of tangency, I'll label it, I don't know, POT, is going to be f of 16 equaling 4. So 16, 4. And I know that my slope, my derivative, well, if f of x equals the square root of x, then you can verify this for me, but f prime of x is going to be 1 over 2 times the square root of x. That's the derivative. So x to the 1/2 power, move the 1/2 down as a coefficient, that's where you get the 2. And then x goes to the 1/2 minus 1, or negative 1/2 power. Bring that down and raise it to a positive 1/2. And I would plug in that c value. So f prime at c would be f prime at 16. So my slope is 1 over 2 times the square root of 16, which is 1 over 2 times 4, which is 8. So I have a point, I have the 16/4, and I have a slope of 1/8, and I'm going to use that to construct a tangent line. Okay, so using this equation and manipulating it, I get that all of this is going to come out to be y equals 15.9 divided by 8 plus 2. Okay, so where did I get that? Well, essentially what you would get is y equals 1/8 times x plus 2. So maybe I should write that down. If I use this idea of point slope, I would get what? I'd get y minus 4, because that's my c value. F of c equals 4, equals my derivative at c, which is 1/8, times x minus c, which is 16. So by simplifying this, I get y equals 1/8 x plus 2, and that is my tangent line. Okay, so then I'm going to use 15.9 to approximate. So if x is 15.9 and I plug that in, then I get 15.9 divided by 8 plus 2. So whatever that equals would technically be an approximate value for this function. So this tangent line g of x, I showed that to be 1/8 x plus 2. That's the equation of this line. And if I plug in 15.9, I get a value that would approximate that function. Okay, so that's fine. That's using tangent lines. Now let's see if we can't use the idea of differentials. Right? So if I use the idea of differentials, I'm essentially looking at this change in y and the change in x. So I want to know what my function value changes by, because I know that it starts out at 4, and I know it's slightly less than 4, but I want to know how much. So with differentials, we already calculated all this scratch work, right? We already calculated the point of tangency, we calculated the slope, so I'm just going to rewrite that. So I know that f of 16 equals 4, so using differentials, f of 16 equals 4, and my slope at 16 is 1/8. Well, I'm going to start out with the definition of the derivative using Leibniz notation. Dy dx equals f prime of x. If I multiply both sides by dx, if I want to find this change in my function value from 4, then I take the derivative at some c value, okay, but I'm going to call it x right now, times dx. Well, what is my change in x? Well, if you look at it, I start out at 16, that's where my derivative is defined, And then I'm altering it by how much? Well, I'm altering it by 0.1 because I want to approximate 15.9. So I start from 16 and I actually subtract 1/10. Okay. So essentially my dx ends up being 0.1. So dx equals 0.1. And what is the derivative at that point? Well, it's 1/8. So this ends up being a really easy problem because all I have to say now is that dy equals 1/8 times 1/10, which is 1/80th. Okay, so think about that. That is my change in y. I just calculated that with this picture, if I change by 0.1, my y changes by 1/80th. So if I start out at 4, I know it's going to be slightly less than 4, and I calculated exactly how much. So an easier way of approaching this, in my opinion, is to say, well, I'm going to start at 4. My actual y value of 15.9 is starting out at 4, and then subtracting this infinitesimal change in y, which ends up being 1/80th. Right? So in my opinion, if you're a mental math kind of person, this is much easier to do than 15.9 divided by 8. 15.9 divided by 8 plus 2. So there's the idea of differentials. Okay, so I want to look at how that would be applicable in like a real life situation really quickly. So suppose that, I don't know, you're a really big fan of Hasbro games, so Hungry Hungry Hippos, and you have all these marbles, and you're a factory manager, and you want those marbles to have a consistent volume. Well, you can't make sure they all have the exact same volume, okay? According to life and principles, they're all going to vary by certain amounts. But you don't want the volume to vary too much, or maybe the gameplay is going to be shifted a little bit because the marbles will be weighted. So I want the volume to be within 0.15 cubic centimeters. Okay, so maybe an average marble, you took an average of all these marbles and you discovered that they should have an average of about 2 centimeters for the radius. Now I want to know how much this radius can vary to be within these parameters. Well, hopefully you know that in Hungry Hungry Hippos, all these marbles are roughly spherical. They're roughly spherical, so what I can end up saying is, since these marbles are roughly spherical, I have a way of comparing the volume to the radius. Because the volume of a sphere can be given by the equation v equals 4/3 pi r cubed. If you don't know that, then memorize it. Thanks. So volume equals 4/3 pi r cubed because it's roughly spherical. If I take the derivative of both sides, you can do this one of two ways. You can notice that your input variable is r, and then take dv dr with respect to r. Just like if your input was x, you would take dy dx. Or you could just technically take the derivative of both sides. Apply the derivative operator. So if I apply the derivative operator to v, I get dv. Okay? And if I apply the derivative operator over here, then I use the power rule. If I use the power rule, I'm eventually going to get 4 pi r squared. But then I multiply that by the derivative of r, dr. And if you want to check to make sure that that makes sense, divide both sides by dr, and you get dv dr equals 4 pi r squared. So you can do it one of two ways. You can do it that way, or you can do dv dr and multiply both sides by dr. So I'm looking at how much my radius can vary to get a variance in the volume. Well, I just said that I want the volume to differ by no more than 0.15 cubic centimeters. So my change in volume then would just be 0.15. Okay? And on average, the radius is given to be 2. So maybe I should highlight this. The radius is given to be 2. So I know that my radius is just 2. And I can solve for dr. Okay, so what I'm going to end up getting is that 0.15 equals 4 pi 2 squared. Okay, so that's going to be 16 pi times dr. And by manipulating both sides, I get that dr is 0.15 divided by 16 pi, which is approximately 0.003 centimeters. All right? So I'm actually going to take that a step further. I'm going to take it 2 steps further. The first thing I'm going to do is say, well, my radius at 2 centimeters is plus or minus 0.003. This is how much it can vary both ways, okay? It could be bigger than by within this much, and it can be smaller than within this much. So if I started at 2, it's plus or minus 3 thousandths, then I'm going to have 2.003, okay, and 1.997. But even more applicable than that, if that's what my radius is, then I can find out what my diameter can vary by. Right? Why would I need that? I'll tell you in just a second. So my diameter supposedly could vary by 2 times this. Right? Because the diameter is twice the radius. So I know that the diameter is going to be 4.006 as a maximum and 3.994 as a minimum. Okay, so why is this more applicable than the radius? Well, think about how those factory workers are going to measure that marble. I don't understand how you could just measure the radius. What you could probably do is you could take something like a vernier caliper and measure this distance. Okay, if you measure that distance, that would be the diameter. So this is more easily expressed in terms of the diameter. Okay, so what you could actually do from the beginning is you can, instead of the radius, you could just plug in d divided by 2, but that introduces like d cubed over 8, and it just introduces a bunch of unnecessary math. So I think this derivative and this differential is easier, and then just double this. All right, so that's how you'd approach it. Okay, last thing I want to show you really quickly is some more derivatives of transcendentals. Okay, we'll learn how to prove these eventually, but I just want to show them. If I take the derivative of some base a raised to the x power, so my base is constant, let's say it's like 3 or pi or a number raised to a variable, so it's an exponential function where my input changes, the derivative is the natural log of that base times a to the x. So you get this back, you get this quantity back, it's the same thing. You just have to multiply it by this factor, natural log of a. Okay, so a really nice example is if my base a equaled the constant e, okay, Euler's number e, okay, then I'm taking the derivative of e to the x, which is the natural log of my base e times e to the x. Well, the natural log of e is defined as 1. Okay, so the derivative of e to the x is e to the x. It is the only function whose derivative is the same thing as the function, which is pretty cool. And I can do the same thing with number 8 right here. If I take the log with base a of x, I'm kind of doing the same thing. I'm getting 1 divided by x, but I have to multiply it by 1 divided by the natural log of a. So if a equaled e again, I'm taking the derivative of log base e, which is the natural log of x, which is 1 divided by the natural log of e times x. Well, again, the natural log of e is just 1, so this evaluates to 1 over x. So these are the most common that you're going to see, but I highly recommend memorizing this and being able to apply it from having a base of e to any base. Right? All right. So that is our lesson on differentials and tangent line approximations, and I hope that was helpful.